Yes. So we're continuing the discussion of eigenvalues and eigenvectors. So we have a linear operator. That means a linear transformation from a vector space V to itself. We say that lambda is an eigenvalue for this operator T if there's a non-zero vector V such that, oops, make sure everything gets in here. If there's a non-zero vector V such that T of V is lambda V. And we say that a subspace W of the vector space is invariant under T or T invariant if T maps W into W. If you take any vector in W, T sends it to some other vector. Could be the same, could be different, but it has to be inside of the subspace W. And in particular, every eigenvector generates a one-dimensional invariant subspace because what a linear operator does to an eigenvector is just scalar multiply it. Just stretches it, but it doesn't change its direction. So a basic example of a linear operator is just a square matrix, an n by n matrix. And this defines a linear operator T sub A from Rn to Rn by just vector multiplication. T of V is the matrix A times V. So as a simple example, take this 2 by 2 matrix 1, 1, 0, 1. So if you multiply this by the vector, if you apply this to the vector xy, that's the matrix A times xy. Here's the matrix, here's xy. You do matrix multiplication, you get x plus y, y. And this, so xy is an eigenvector with eigenvalue lambda. Of course, it has to be a non-zero vector. And if you apply A to xy, well, that's just lambda times xy. If this is an eigenvector with eigenvalue lambda, that's lambda x, lambda y. So when you equate these two expressions, you get this equals this. So x plus y is lambda x and y is lambda y. Now, it could be y is different from 0. And in that case, you can cancel the y and you get lambda equal to 1. In the second case, y equals 0. But then the first equation says, so if y is 0, x is not 0 because the vector is not the 0 vector. And x plus y is just x if y is 0 is lambda x. So in this case also, lambda equals 1. So the only eigenvalue for this matrix is 1. And how do we find an eigenvector? Well, T sub A of xy, which is x plus y, y, that has to be equal 1 times xy, namely just xy. So this says y equals y, x plus y equals x. That says y has to be 0, and x can be anything. So the only eigenvectors are the vectors with the y coordinate equal to 0, x comma 0, which is just x times the vector 1, 0. So the space of eigenvectors for the eigenvalue 1 is just the set of scalar multiples of this unit vector in the x direction. So this linear operator only has one eigenvalue. And you'll see in the notes more explicit calculations of eigenvalues for particular matrices. Now, I proved yesterday some general theorems about eigenvectors and eigenvalues. And so theorem 1 says the following. Suppose we have t from V to V is a linear operator with eigenvalue 0, lambda equals 0. Sorry, with eigenvalue lambda. Let's look at the general case first. So let E of lambda be the set of all vectors in V such that T of V is lambda times V. So then the assertion is E of lambda is a vector subspace. Oops.
Yeah, thank you.
A subspace of V. And there'll be a second condition, but I'll write that down in a moment. Well, right. Or moreover, E of lambda is exactly the kernel of the linear operator lambda sub I minus T. Remember, I is the identity operator. I of V equals V for all V. In terms of a matrix, if you take the identity matrix, which is zeros down the main, ones down the main diagonal and zeros everywhere else, this is the identity operator. You can add and subtract linear operators. In fact, we show that the set of matrices, which is the same as the set of linear operators, is a vector space. So this is a linear operator, and E of lambda is the kernel of that. How do we prove this? I proved yesterday that E of lambda is a subspace. Of course, if I can prove that E of lambda is the kernel of this linear operator, then that automatically implies it's a subspace, because the kernel of a linear transformation is always a subspace. So let's say, so lambda is an eigenvalue with eigenvector x if and only if eigenvector v, if and only if T of V is lambda times V. V, that's lambda, V is the same as the identity operator applied to V, because I of V equals V. If I bring this on the other side of the equation, that says T of V minus lambda I of V is 0. But T of V minus lambda I of V, that's the operator T minus lambda I applied to V, which means V is in the kernel of T minus lambda I, or I should have done the, this is absolutely correct, but I should have done the subtraction the other way. If T of V is lambda IV, that means 0 is lambda I of V minus T of V, which is lambda I minus T of V. So this is an operator. Lambda of it, this operator applied to V gives 0. So V is in the kernel of lambda I minus T. The kernel of every operator contains 0. And V is lambda is an eigenvalue precisely when the kernel is bigger than 0. There's some non-zero vector in here. So in particular, lambda is an eigenvalue of T if and only if the kernel of the operator lambda times the identity minus T is not just the 0 vector. The kernel always contains the 0 vector. If it contains something else, then lambda is an eigenvalue. If it doesn't, then lambda is not an eigenvalue. And E of lambda is called the eigenspace associated with the eigenvalue lambda. Now, there's a very simple property of eigenvalues and eigenvectors that I also proved yesterday morning, which is the following. So theorem, let lambda 1 up to lambda k be a set of distinct eigenvalues of the linear operator t, let v1 up to vk be associated eigenvectors. That means t of lambda, t of v sub I. So if you apply t to the eigenvector v sub I, you get the eigenvalue lambda I times v sub I for all I going from 1 up to k. And the conclusion is this set of eigenvectors is linearly independent. So I'm not going to repeat the proof, which I did yesterday and which is in the notes, or will be in the notes that you get. But there's a very nice corollary of that, because if the dimension of your vector space is finite, then if you look at the spectrum, so the spectrum of an operator T is the set of all eigenvalues of T. So if the dimension of V is finite, then and this is denoted sigma of T. So this is our standard notation for the spectrum of a linear operator T, which means the set of all the distinct eigenvalues. And if for every eigenvalue you have an eigenvector and that set of vectors is linearly independent, you can't have more linearly independent vectors in a vector space than the dimension. So the cardinality of the spectrum, right, absolute value signs around the set mean cardinality, or number of elements, is less than or equal to the dimension of V. So that's a nice corollary of this theorem. One other remark is the following. Every eigenspace E of lambda is a T invariant subspace. So what does that mean? We must show that if V is a vector in the eigenspace, then that implies that T of V is also in the eigenspace. T can move these eigenvectors around, but it can't move them out of the eigenspace. So, and the proof is really just one line. If V is in the eigenspace, that means T of V is lambda V. If you apply T to this, T of V is T of lambda of V is lambda T of V. So if you apply T to the vector T of V, you get lambda times T of V. So T of V is also an eigenvector, which means it's in E of lambda. So this is an extremely simple proof once every single symbol is clear and justifiable to you. And again, this is one of the many things you need to spend time at home alone thinking about in order to understand. Let's look at the special case of R2. So the study of the eigenvalues of an operator T, or equivalently the spectrum sigma of T of the operator T, is called spectral theory. So in mathematics in general, and in linear algebra in particular, spectral theory is the study of linear operators from the point of view of their eigenvalues and eigenspaces. So let's do spectral theory in R2. So again, if you have a 2 by 2 matrix A, B, C, D, this, call this A, you have this linear operator T sub A of xy, which is just the matrix times xy. That's ax plus by, cx plus dy. And if xy is an eigenvalue, so in the eigenspace of some eigenvalue lambda, that is, if T of xy is lambda times xy, well, here's T of xy. This is going to be lambda times xy, which is lambda x lambda y. So this gives us two equations, two linear equations. Ax plus by equals lambda x, and cx plus dy equals lambda y. So lambda is an eigenvalue. If you can find a non-zero solution of these two equations, actually, I have an x on both sides, so let me put everything over on one side. So my first equation would be lambda x minus ax minus by equals 0, or I can write that as lambda minus ax minus by equals 0. And my second equation, if I bring everything over to the other side, I get minus cx plus lambda y minus dy, which is the same as minus cx plus lambda minus d times y equals 0. So this little set of high school algebra equations is really very important for us. We have a 2 by 2 matrix A, B, C, D, which sets up a linear operator on R2. The operator applied to xy is just the matrix times xy. So the vector xy goes to this matrix. Now, if this vector is an eigenvector with eigenvalue lambda, this is simply equal to lambda xy, which is lambda x times lambda y. So equating coordinates, ax plus by equals lambda x, cx plus dy equals lambda y. That's these two equations. And if I just rearrange it to collect the x's here and the y's here, I get lambda minus ax minus by is 0, and lambda and minus cx plus lambda minus dy equals 0. And what can we say? Lambda is an eigenvalue if and only if this system of equations has a non-zero solution. And again, equations, two equations in two homogeneous equations and two unknowns have a unique solution precisely when the determinant of the coefficients is 1. So lambda is an eigenvalue if and only if these equations have a non-zero solution. So if and only if this times this, lambda minus a, lambda minus d, minus b times minus c is bc, is equal to 0. Or if I rearrange this, this is lambda squared minus a plus d lambda plus ad minus bc equals 0. So I get that if you have the matrix A, B, C, D, lambda is an eigenvalue if it's a solution of this quadratic equation. And it's a very interesting quadratic equation because the constant term AD minus BC is just the determinant of A. And if you have this matrix A, B, C, D, in a matrix, the sum of the elements on the main diagonal is called the trace. So as it turns out, this is minus the trace of A. That's just a word, it's just a name, but this is the quadratic equation. And this is really an if and only if statement. If this equation has a non-zero solution, then these two equations and two unknowns have a non-zero solution, and xy is an eigenvector. Let's see, so let's try an example. So the problem, a problem in spectral theory is given a linear operator, what are the eigenvalues and what are the eigenspaces associated to each eigenvalue? So let's give one which is actually kind of a counterexample. Suppose A is the matrix 0, 1, minus 1, 0. If you take the unit vector E1 equal to 1, 0, what does A apply to E1? That's A times 1, 0. That's 0 minus 1, 1, 0. Applied to 1, 0. That's 0, 1. So E1 gets rotated 90 degrees, or pi over 2, to E2. E2 is the vector 0, 1. What is A of E2?
Do you bring the paper later down, please? Thank you.
What is A of E2? Here's my matrix. Applying it to E2, which is 0, 1, I get minus 1, 0. So E2 gets sent to the, which is equal to minus E1. So E2 gets rotated over there. And in fact, geometrically, this matrix corresponds to rotation by pi over 2 radians, or 90 degrees. Every vector gets rotated by 90 degrees. So that means that A changes the direction of every vector. Remember, if you have a vector and it's an eigenvector, when you apply A to it, it just stretches it in one direction or the other. But here, A applied to any vector rotates it by pi over 2. It doesn't stretch it. So it changes the direction of every vector. Therefore, just geometrically, A has no eigenvalue. So I just gave a geometrical proof of this fact, but we can also prove it using the quadratic equation. So in general, well, lambda is an eigenvalue if lambda is a root of the polynomial. Let me use t as my variable. Well, I'll just use lambda I minus a, determinant of that. Right? Lambda I is lambda 0, 0, lambda. A is a, b, c, d. So we get lambda minus a minus b minus c lambda minus d. And this determinant is exactly the polynomial lambda minus a, lambda minus d minus bc, or lambda squared minus a plus d lambda plus ad minus bc. Now, we're looking at the matrix A equal to 0, 1, minus 1, 0. So this is A, B, C, D. So lambda squared minus a plus d is 0. 0 times lambda plus ad, 0, minus bc. Bc is minus 1, plus 1. So my polynomial is lambda squared plus 1. And lambda squared plus 1 has no real roots. So if it has no real roots, it has no eigenvalues. That's the algebraic proof of what a moment ago we had proved geometrically. Let's look at another example. Suppose I have the matrix A equal 3, 1, 2, 4. So then lambda I, or I lambda, lambda I minus A, that's lambda 0, 0, lambda minus 3, 2, 1, 4. So this is the matrix lambda minus 3 minus 2 minus 1 lambda minus 4. And the determinant of this matrix, AD minus BC, lambda minus 3 lambda minus 4 minus 1 times minus 2, which is 2. So this is lambda squared minus 7 lambda plus 12 minus 2 plus 10. And I can see this factors. This is lambda minus 2 lambda minus 5. And that's equal to 0 if and only if lambda is 2 or 5. So the spectrum of this operator A is just 2 and 5. Let me find the corresponding eigenvectors. So let's compute an eigenvector for the eigenvalue lambda equal 2. That means that A times xy, which is 3, 2, 1, 4 times xy, that's 3x plus 2y, x plus 4y when you multiply. This is supposed to equal 2 times the vector xy, or 2x, 2y. In other words, x and y have to satisfy the equations 3x plus 2y equals 2x, or x plus 2y equals 0, and x plus 4y equals 2y, or x plus 2y equals 0. So they're the same equation. X and y just have to satisfy this. This says x is minus 2y. So if I take xy, if I take y to be 1, x would be minus 2. So this is an eigenvector. For lambda equal 2. Let's just check. If I take A times the vector minus 2, 1, that's 3, 2, 1, 4, minus 2, 1. That's minus 6 plus 2 is 4. Minus 2 plus 4 is 2. Oops, let's see. Minus 6 plus 2 is minus 4. Minus 2 plus 4 is 2. This is exactly 2 times the vector minus 2, 1. So A applied to minus 2, 1 is 2 times minus 2, 1. So this is the eigenvalue. A of this vector is just a scalar multiple of the vector. And similarly, we can compute an eigenvector for the eigenvalue 5. And there are quite a few examples in the notes that I'll send out probably tomorrow. Let me show a connection between matrices and linear operators. And maybe for simplicity, I'll just only look at the vector space Rn. So suppose that T, now I'm no longer looking just at a linear operator, I'm looking at a linear transformation. So it can go from Rn to Rm, dimension n, dimension m, and they don't have to be the same. So this is a linear transformation. And suppose Rn has a basis, any basis, I'll just call it B, consisting of n vectors, E1 up to En. And let's say Rm has a basis B prime, consisting of m vectors, which I'll call F1 up to Fm. So for each I from 1 up to n, T of this basis vector EI is a vector in Rm. So T of EI, let me call this J. T of EJ is some linear combination, I going from 1 to m, of the basis vectors in Rm, and let me call these coefficients Aij. So T of Ej is a linear combination of the m basis vectors F1 up to Fm. So I goes from 1 up to m. Now, suppose I take any vector v in Rn. So V has some coordinate matrix with respect to B. So to say that square brackets VB is the vector x1, x2 up to x sub n, what this means is that the vector V is this linear combination xj, ej, j goes from 1 up to n, right? Every vector in Rn is a linear combination of vectors in the basis. This doesn't have to be the standard basis. It can be any basis. So V is some linear combination xj, ej. But each ej is a linear combination t of ej of these f's like this. So what is t applied to the vector v? So t applied to the vector v is t applied to the vector summation j goes from 1 up to n, xj, ej. This is summation j goes from 1 up to n, xj, t of ej, just by the linearity of t. And t of ej I can write as a linear combination of the f's. This is summation j goes from 1 up to n, xj, summation I goes from 1 up to m, aij, fi. And I can interchange finite summations. This is summation I goes from 1 up to m, summation j goes from 1 up to n, aij, xj, or xj, aij, they're the same, aij, xj times f sub I. And when I interchange summations, I see I have the vector f sub I. I have a linear combination with these as the coefficients. So let me write that down on another piece of paper. So if V has coordinate vector x1 up to xn, this means that the vector V is summation xj, vj, j goes from 1 up to n. That's what that means. T of V, this is the vector summation I goes from 1 up to m. Summation j goes from 1 up to n, aij, xj, times the vector f sub I. So this is the vector in Rm whose coordinate vector has these as coordinates. That is, with respect to this basis B prime in Rm, the coordinates are summation j goes from 1 up to n, a1j, xj, summation j goes from 1 up to n, a2j, xj, down to summation j goes from 1 up to n, a mj, xj, anj. Am, m-dimensional. But if I look at this, this is exactly the vector I get if I take the m by n matrix, a11 up to a1n, a21 up to a2n, am1 to amn, and multiply that by this vector xn. This is what I get. So what I have is, once I choose bases for v and w, if I take a vector v, the coordinate vector for t of v with respect to b prime is this matrix A, and this x1 up to xn That's the coordinate vector for v with respect to b. So this somewhat perhaps obscure looking formula is really one of the basic facts in linear algebra. It says if you have a linear transformation from one finite dimensional space to another, let's say from an n-dimensional space to an m-dimensional space, then there's always a matrix A, which applied to the coordinate vector of v gives you the coordinate vector of t of v. Let's look at an example. Let's make it simple. Suppose I look at an operator t from R3 to R3, and suppose I use the standard basis for both of them. And suppose that t of E1 is 2E1 minus E2 minus E3. And t of E2 is 3E1 plus 2E2 plus 7E3. And t of E3 is 6E1 minus E2 plus 4E3. So this is just some operator from R3 to R3. And so let me call the standard basis script E. So the coordinate vector for t of E1 is what? Well, this is 2E1 minus, this is the vector 2 minus 1 minus 1. This is the vector 3, 2, 7. This is the vector 6 minus 1, 4. So t of E1 is 2 minus 1 minus 1. T of E2 is 3, 2, 7. T of E3 is 6 minus 1, 4. These become the columns of our transformation matrix. A is the matrix 2 minus 1 minus 1. Second column is 3, 2, 7. Third column is 6 minus 1, 4. And if you take any vector v, which has coordinates x, y, z, then t of v is just a times x, y, z. Now, the only way really to get a feeling for what is going on is to work a lot of problems. So in the homework that I'll send out, again, probably tomorrow, the homework for Monday, it will have problems about spectral theory, about eigenvectors and eigenvalues, and also problems about how to construct the matrix, which defines a linear transformation from one finite dimensional vector space to another. So there'll be some additional notes, and over the weekend, you'll get homework for Monday, Tuesday, and maybe Wednesday. And the final exam, as you know, is 1 week from today. is Thursday, July 1st. And Thursday, July 1st. Any questions about anything that I did today? There's a lot to learn. There are new concepts in this a lot, so it takes a bit of work.
So the final exam is just gonna be everything we've learned thus far plus eigenvectors and eigenvalues, right?
No, so if you think of this in terms of a regular semester, one more week means the equivalent of a month in a semester. And there's one other topic we're going to cover, which I'll talk about on Monday, which is inner product spaces. So in advanced calculus or Calc 3, when you were looking at vectors in R2 or R3, you had the dot product of vectors. So, and you could talk about the length of two vectors and the angle between the vectors. And we haven't done that yet. So the next topic, so the last topic we're going to cover after eigenvalues and eigenvectors is, so in calculus it's called the dot product, but more generally in linear algebra it's called the inner product. And so on Monday and Tuesday I'm going to be talking about the inner product. And that's the last topic on the syllabus.
Also, like the inner product and dot product, you do them the same way, right?
Yeah, so you remember in calculus, you usually write your vectors horizontally instead of vertically. So if you had like x1, y1, and x2, y2, the dot product was x1, x2 plus y1, y2, right?
Mm-hmm.
So that's the dot product, which in linear algebra is called the inner product. But in 2 dimensions, it's exactly the same thing. So what we talk about in linear algebra is a simple, straightforward generalization of the dot product that you're supposed to have seen in Calc 3. You know, in Calc 3, you also see the vector product. If you have 2 vectors in 3-dimensional space, there was also the vector product of them, which was, see, the thing is, when you have a dot product, you can talk about 2 vectors being perpendicular. And you can talk about the length of a vector. So if you have a vector v, it has a length. And if you have 2 vectors, you can also talk about the angle between vectors. So in Calc 3, you did all this using the dot product. And in general, for any vector space, we do it using, essentially it's the same thing, it just has a different name. It's called the inner product. And the inner product allows you to determine the length of a vector, the cosine of an angle between vectors, whether 2 vectors are perpendicular and so forth. So that's the last topic in linear algebra that we're going to cover.
Okay. Professor.
Okay.
Professor.
Yes.
Is the final cumulative?
Yes.
So that's everything that we learned since the beginning of this semester, right?
Correct.
All right. Thank you.
Okay. That is it.